radius n and n plus dn are between the energy levels E and E plus dE. So for example, I go to take subtract these two things. Okay, so that is the energy or number of available energy states, number of available energy states in between that n plus dn and n are that is equal to the number of available energy states in between the energy levels E and E plus dE. Are you understand this? Yes. So now you go to take the difference. For example, 1 by 8 common for both. I go to take 1 by 8 outside. 4 by 3 pi n dn cube minus 4 by 3 pi n cube. So the difference between these two, that is n plus dn and n, the difference gives the number of available energy states between the shells n and n plus dn or between the two energy levels E and E plus dE. Are you understand? Yes. Yes.
Yes, sir.
Okay. So this available energy state. So this available energy state in between the energy interval, you say that is Z of E dE. So now I go to take here, see the number of available energy states. So now I go to replace the term by Z of E dE. That is the density of state. Already you discussed in the definition. So the Z of E dE is equal to 1 by 8 times of 4 by 3. Now I go to take pi is also outside, common outside. I go to expand this, that is a plus b whole cube. So what is the expansion for that a plus b whole cube? Anyone? Expansion?
A square plus b square plus 2a square b plus 2ab square.
A cube here, that is a plus b whole cube.
A cube plus b cube
A cube plus b cube plus
3ab square.
3ab square plus 3 yes. So see here, n cube dn cube plus 3n square dn plus 3 dn square minus n cube. Is it correct? Yes.
Yes, sir.
Yes. Now any terms get cancelled here? Please check.
N cube.
Yes, plus n cube and minus n cube get cancelled. Then the dn cube, see here the dn cube dn square, that delta n, the dn is too small. That is too small. So if you go to take the cube or square, so definitely that is also value is too small. That's why I go to neglect the higher terms of dn, that is dn square, dn cube, etc. So now my second term, that dn cube and the 3n square dn term, see here. Okay, some terms are get cancelled. Which one? The dn cube term and the 3 dn square n. So these two terms get cancelled. Yes.
Yes, sir.
So in the this equation, see that n cube and this minus n cube get cancelled, and again I go to neglect. See here, since the high powers of dn is very small, so that's why I go to dn square and dn cube can be neglected. So here dn cube, that is my second term, and dn square, that is my fourth term. So our four terms are okay, simply they get cancelled. So now I go to only the term is 3n square dn term is there. So that's why I'm writing here z of e dE. So 1 by 8 into 4 by 3. So that is 1 divided by 8, 4 by 3. So you go to get cancelled. Okay, 4, 8. How many times? So 2 times. Simply you go to take pi by 6. Pi by 6, 3n square dn. Is it correct? Yes? See, yes or no? Check. Yes.
Yes,
Then
sir.
because then once again I go to simplify it. I go to take 3 outside. Already pi by 6 is there. Okay, again pi by 2, 3, 6, they get cancelled. So pi by 2, n square dn. So what is n here? What is n? What is n?
radius of the
Radius.
sphere.
Radius of the
So
sphere.
radius of the sphere. Okay, oh, no problem. So that is n square and dn. That is also the small value. So now you come to the equation, energy equation. I think you studied in the 12th standard physics. You go to derive the energy of electrons in nth orbital. Are you remember? Yes. Anyone?
Yes, sir. Yes, sir.
Yes. That En is equal to nothing but n square h square by 8m l square. I think you remember this equation. Okay. So E is the energy of electron in the nth orbital. For example, the L is nothing but the side. So the energy is given by that E suffix n is equal to minus the negative sign indicates that energy. Okay. So leave it that one, and n square h square by 8m l square. So from this equation, so I go to take rearrange n is nothing but, so what about n here? So what about is n? What is the n here? That is integer, it can take 1, 2, 3, 4, 5 like my energy levels. Energy 1, 2, 3, 4. So now our aim is go to see that is a n square. So in that n square also the sphere. For example, I go to consider the shell. The radius of shell is n. So now I go to rearrange this equation. So I get n square is equal to minus 8ml square e by h square. Is it correct? Yes.
Yes, sir.
Or n is equal to, simply go to take, therefore n is equal to root of, so instead of I am taking root, I put whole power 1 by 2, that 8ml square e by h square whole power 1 by 2. So this is n, this is n. So now n square is there and n is also there. Now you go to differentiate equation 3, differentiating. For example, I go to take the partial differentiation. So my left hand side is dn. So what about the right hand side? Which quantity only? I think most of the quantities are remains constant. So which one is variable quantity here in the right hand side? Anyone?
Energy.
Energy. Yes. So all 8 m l h. 8 is a mere number, m mass of electron. You go to take h Planck's constant, side l. So all are remains constant. So only variable is e. So simply if you go to take differentiation here, so my left hand side is dn. So what about right hand side? What about your right hand side?
So 1
Yes.
by 2 e to the power minus 1 by 2.
So for example, here I go to take differentiating the equation. See here that the equation 2, I go to differentiating here equation 2, that n square. So I go to take here 2n dn more. So my right left hand side is that is n power x. So simply x into n power n minus like that. So 2n into dn. So what about right hand side? 8m l square by h square. So dE, this is the variable quantity. I put dE here. That's all. That is only the variable quantity dE. Okay. Yes.
Yes, sir.
Okay. Now again I go to simplify this. So n into dn. I go to take 2 this side. So 8m l square by 2 h square dE. This is n dn. Why I go to take like this? Because you go to see here. The z of e d is equal to pi by 2 n square dn. So now I go to write this equation n square dn, n into n dn. Is it correct? Yes. So n into n dn. So definitely you get n square dn. So that format. So now I go to see here. So the z of e de is nothing but pi by 2 n square dn. So simply I go to rewrite the same. The z of e de that is equal to pi by 2 n into n dn. Is it correct?
Yes, sir.
Yes. Yes. See that z of e d is equal to pi by 2 n square dn, or the z of e d is equal to pi by 2 n into dn. So the term only I go to write it here more, that n into dn. So now I go to substitute that n dn is coming from this equation, and n already equation is there, where equation 3, that equation 3 gives n, and remember that this equation, I think this equation 5 gives that n dn. I substitute both in this equation. See here in this equation I go to take the z of e de is equal to pi by 2. So 8m l square e by h square whole power 1 by 2, that is n, and n dn is given by this one, that 8m l square by 2 h square de. Any doubts here, please? Anything else or any doubts? Yes. Okay, so now what are the common terms here in both the cases? See, this is 8m l square e by h square whole power 1 by 2, and this is 8m l square by 2 h square de. Some common terms is there. So what are the common terms? 8
ML by
m
2.
8 and
l square
h square.
h square. So this is power 1 by 2 and this is power 1. So 1 by 2 plus 1. So what is the power now? 3 by
2.
yes. In the next step, see, I go to take the 2 outside. Already pi by 2 is there. So now I go to take 2 also. That is pi by 4. 8 m l square by h square whole power 3 by 2. Then that e power 1 by 2 into de. So that is the term. I go to rewrite the above equation by this. I think the z of e d is equal to pi by 4. Pi by 4. Then common terms is there, that 8 m l square by h square. Here power is 1 by 2. Here is power is 1. So simply I go to add both the powers. I get 3 by 2 e power 1 by 2 into de. Then again, once again, I go to take L square. See, this is L square is there more. I go to take L square outside, or simply I go to substitute the power here 3 by 2. That 2 get cancelled, you get L cube. Is it correct? Is it correct?
Yes, sir.
L cube.
Yes, sir.
So that L is nothing but the side. Okay. So for example, I go to take that L cube. It gives definitely volume. Is it correct? Is it volume? Volume of the that for example, I go to take the cubical structure. For example, I go to take the side L. So what is that length, breadth, height? That is L into L into L, L cube. So definitely that gives the volume. So that is the next step. See here, the next step, I go to take L square outside, out of this 3 by 2. 2 get cancelled, you get L cube. So that is pi by 4, 8 m by h square, whole power 3 by 2, L cube, e power 1 by 2 into dt. So what is the L cube gives? The L cube is nothing but the volume. If L is equal to 1, for example, I go to take that is unity. So what about L cube? See, for example, I go to take L is equal to 1 meter. So what is L cube now? L cube. So 1 into 1 into 1, you go to multiply all simply you get 1 cube. So that is per unit volume. What is the meaning of per unit volume? So that is 1 meter. For example, I go to take 1. So that Z of E dE, Z of E dE. So that L cube represents the volume of the metal piece. If that L cube is equal to 1, so that is per unit volume. Per unit volume, the number of available energy states per unit volume. The number of available, that is our aim. The number of available energy state per unit volume, or that is the density of state. The Z of E dE is pi by 4, 8 m by h square whole power 3 by 2, e power 1 by 2 into dE. Are you understand? Say yes or no more. Are you understand or not?
Yes, sir. Yes, sir.
Yes.
Yes, sir.
So this equation 5
Yes, sir.
gives that equation 5 gives the density of state. The Z of T d is equal to pi by 4, that 8 m by h square whole power 3 by 2 e power 1 by 2 into d. But so here I go to take two more concept. So for example, this is electron. Okay, you say that is two type of spin quantum number is there. Electron. I think you remember there are 4 quantum numbers. So principal basic principal quantum number, then azimuthal, magnetic quantum number, and spin quantum number. So what about the spin quantum number? How many? What is the value for spin quantum number? Any idea? How many values you can take?
So plus one,
Well,
minus one, minus one.
Only two
Plus
states.
Plus
Plus
half,
off and
minus
minus
half.
off. Yes, plus off and minus off. Very good. So clockwise or anti-clockwise. Now since that each energy level, please understand that each energy level provides 2 electron state. So one with the spin up, the other with the spin down. Is it correct? Yes. There are 2 that each
Yes, sir.
energy levels. Say for example, the Boyle's exclusion principle. I think you know. Okay. Basically, you studied in this Boyle's exclusion principle. So what is he said? No two electrons having the 4 set of quantum numbers. So where that they go to vary, especially in the spin quantum number. For example, I go to take 0, 0, 1 or 1 plus 1 by 2. What about the next? So 1, 0, 0 minus 1 by 2. So definitely that plus and minus off. So each states or each energy levels provide 2 electron state. That is, one is up and the other one is spin down. Spin up and spin down. So now you go to take the equation 5 is the number of available energy states per unit volume. Again, with come to this concept, each level provides 2 electron states. So simply I go to multiplied equation 5 by 2. So that is the density of state in that energy levels. Are you understand this? Yes. So why I go to multiplied here 2?
Yes, sir.
Because that each electrons, that each state gives 2 set of available energy states, but we do not know whether it is plus off or minus off. But anyway, so definitely 2 states are available, plus of states and minus of state. So that's why I go to multiplied by 2. That equation 5 multiplied by 2, we get the number of density of state in both either spin up or spin down. Is it correct? Yes.
Yes, sir.
Yes, sir.
Sorry. Yes. Any doubts? Any doubts here? Please. Any doubts? Please go to. No.
No, sir. No, sir.
Okay. Okay. See here now. That is 2 into pi by 4. I think we get pi by 2 here. So pi by 2. Pi by 2. That 8 m by h square whole power 3 by 2 e power 1 by 2 d is there. Again. See that Z of E dE pi by 2. That 8 m by h square whole power 3 by 2 e power 1 by 2 d. That equation 6 gives the same density of state. Equation 6 gives the density of state in the available. But so already you consider that is a sphere of volume, that is 1/8 of it arctant. Is it correct? So what is the total number of available state now? How you go to calculate? See, for example, I need a number of available state in the whole sphere. So how you go to take that one?
Into 8.
Maybe for example, that is you multiplied. So this is only in that energy levels. In that energy levels, so you get that is pi by 2, 8m by h square whole power 3 by 2 e power 1 by 2 de available energy states in that particular energy interval. That is the energy interval is de here. Please understand that the energy interval is de. So equation 6 gives the density of states or the number of available energy states, number of both, either spin up or spin down, because that each states provide the 2 electron state. So the number of available state in that energy interval de is given by this equation, that pi by 2 into 8m by h square whole power 3 by 2 e power 1 by 2 into de. I think almost you understand now. Is it correct? Check. Yes.
Yes.
Say yes or no more.
Yes, sir.
Yes, sir.
But
Yes,
see
sir.
that
Yes, sir.
end of
Yes,
the lecture.
sir.
See, end of this
Yes,
lecture,
sir.
I will share this that PDF. Okay, no problem. If you have any doubts or clarifications, so the next class, for example, before you start in the next class, at least you go to clarify in future that every classes first 5 minutes you go to take the clarification for prior classes. That's all, because there are lengthy derivations are there. So this also the one more derivation in the next lecture is also one more lengthy derivation. I think some confusions is there. Okay, so now that z of e de is pi by 2, the 8m by h square whole power 3 by 2 e power 1 by 2 into de. So now again you go to rewrite this equation also. Sometimes in some books, the reference books, they go to take m is also outside. So instead of they are writing put into m in the okay, so they go to take m common outside and put some more equation. There are different equations also there. But anyway, the expression is same. That z of d is equal to this expression is same. That's all. So this gives, or equation 6 gives the density of states of electrons. Any doubts or clarifications, please? Anyone? Any doubts or any clarifications, please? No. Anything else?
No, sir.
Okay, ma. So now I move on to the next, the energy bands. So next, that's some simple, that energy bands, how the energy bands are formed. Already the last class I told. For example, I go to take the same sodium atom here, or instead of that, I think I go to take silicon. Ma. What is the atomic number for silicon? Silicon atomic number
14.
14. 14. The electronic configuration is 1s2, 2s2, 2p6. Okay, then 3s2, 3p2. Is it correct?
Yes, sir.
Yes. Okay. Okay. Now, in the outermost orbital, so how many electrons are there? Only 4 electrons are there. So 3s2 and 3p2. Okay. K shell is completely filled. L is also completely filled. In M shell, basically the M there are 18 electrons, but out of 18, only 4 electrons is available now. So that 4 electron goes to where? 3s2 and 3p2. Okay, so the 3s2 shell is completely filled. Please understand the 3s2 is completely filled, and 3p, there are 6 electrons in the p orbital, suborbitals, but only 2 electrons is there. So how many electrons are required to complete the 3p orbital? That is 4 more electrons is available. Yes, 4 more electrons. Now, when the atoms are come closer and closer, what happens? For example, already you see the kinetic theory of gases, but in the gases, there is no doubt the molecules are far away. But so what about solids? Especially what about solids? The intermolecular attractions is more for, because the atoms are come closer and closer. Yes, especially for metals or something, semiconductors or metals. You see, and the atoms, the interatomic distance is too small. The atoms are come closer and closer. So once the atoms are come closer and closer, what happens? That inner shells, you please leave it. For example, I go to take that silicon. The 2K shell is completely filled. Okay, that is one energy level. Okay, then L shell, that is also completely filled. That is 2s2, 2p6. That energy level is completely filled. But only the valence electrons or in the outermost electrons is move revolving in the orbits, so definitely is disturbed when the atoms are come closer and closer. Can you understand this? Yes. See that inner shell, there is no disturbance here, but what about the outer shells? So when the atoms are come closer and closer, see here, if the atoms are initially is far apart, the electrons in the adjacent atoms will not interact with occupy and the discrete energy level, but the atoms brought come closer enough, the outermost electrons definitely interact, and the energy level is splitting. Are you understand here? Yes. Say, for example, I go to take n number of atoms. So here you say only one atom, that is no issue. But for example, here 1 mole of gas contains n Avogadro number. For example, I go to take small, the 1 gram. Also, you get to take n number of atoms. That is a Avogadro number of atoms. So if such n number of atoms come closer and closer, what happens? There's no doubt that the electrons, the outermost electrons or the valence electrons, interact with these other atoms or other atoms, so definitely they go to collapse or coupling takes. So this is a coupling between the two atoms, due to this coupling, so there is no doubt, definitely the energy level is split. See here in the diagram, so this is interatomic distance is for example, how the energy level is split. See, this is a normal case. For this is interatomic distance, and this is a electron energy. So now, if the distances goes on, for example, come closer and closer, see that n is equal to 1 level, there is no use because the n is equal to 1 is completely filled. For example, that is K shell, that is completely filled. I am telling this is for silicon example I am telling. So n is equal to 1 completely filled. So what about n is equal to 2? That is L shell, 8 electron, that is also completely filled because 2s2 2p6, 8 electrons completely filled. So what about my n is equal to 3? K L M shell. So basically in M shell, how many electrons are there? 18, but so only 14 is there, and that 14 also 3s2 and 3p6. 3s2 is completely filled, but 3p out of 6, only 2 electrons is there. So now the atoms come closer and closer. Say the atoms come closer and closer. You see here that 1s2, 2s2, 2p6, then 3s2, 3p2. I think this 4 indicates the 4 more electrons it will require. See, for example, it will come closer and closer. So definitely they go to interact with the neighboring atoms. So 6 allowed energy levels, but only 2 allowed energy levels of same energy. The remaining 4 is also come. So these 4 atoms interact in the equilibrium distance of A0. Same situation whether the other atoms comes closer. So these 4 electrons interact with the remaining 4. For example, is coming with 1 by very close to each other. So 4 plus 4, almost 8 electrons coming. Okay, so that 8 electrons they go to complete that 3s2 and 3p6. Yes, are you understand? Yes, so the splitting of 3s
Yes.
and 3p state. So now due to this, what happens? Due to the coupling, the energy level, that is there is a gradual decrement of, see here. So this is a energy levels is almost splitting like this. See in the above diagram, see this is a normal case. This is a normal case. But when the atoms comes closer and closer, the same energy level, see they are spreading like this. See here. So there are 2n state. For example, lower levels that is completely filled. All the state 2n states are completely filled by 2n electrons. But so what about the higher states here? There are 6n state, but only 2 electrons. That is 2p6. Basically the p s is leave it because 3s is completely filled, but only 3p. There are 6 electrons, but only 2 electrons is there. So there are 6 n states, but only 2 n states are available because 2 electrons only available. So now they go to interact with the neighboring atoms, and the 4 n states. Here is 0 electrons. Once they go to collapse, the same 4 n states. Now there are 4 n electrons here. Are you understand? Yes.
Sir, can you explain it once more?
See, listen. First, go to my left hand side, right hand side. There are initially 3s is 2n state. The number of 2 electrons maximum. So the 2 electrons already filled. So 2n electrons are already filled. So almost all the 3s orbitals are completely filled. There is no doubt. But what about 3p? So 3p, there are 6 electrons, 6 in state. That is 6 electrons. But in the silicon, there is only 2 electrons. Is there? Is it correct?
Yes, sir.
Yes. Now, for example, the atoms are come closer and closer. So the same set of atoms, almost all the atoms are similar in nature. But that is especially the metals and semiconductor. The most probably they are in the crystalline. Okay, so that is the regular and periodic arrangement of atoms or molecules here. So that's why such a the crystalline nature of atoms come closer and closer. See, the available states is here 6n, but the only 2n states are filled. So what about the vacancy states here? 4n states. 4n. If there is no interact with the remainings, okay, neighborings, so there is 0 electrons are, but they go to interact with the neighboring atoms. There's no doubt that the 3s2 also shared with here. See here, that 4n state, this is merging now. So 2 plus 2, the 4n state, and 4 electrons are coming.
Oh, yes, sir.
Yes.
Yes, sir.
Now, that 4n, this is 4n states more, but they coming from where? The 2 electrons coming from p side and the remaining 2 electrons coming from where? N side, the s side. So 4 states is filled now. So now the energy is splitting, that gap. Okay, the energy level is splitting now. So similarly, all the atoms, for example, all the atoms come closer and closer, very close to each other. So these splitting coupling takes place due to the coupling of atoms between or electrons between the two atoms, neighboring atoms. So the discrete energy levels are coming, and see here, these type of energy levels arises here. Yes, understand?
Yes, sir.
So in the energy bands, so that's why
Yes,
you go
sir.
to see how they go to explain that the bands means, because for example, the overlapping in the case of normal conductors, so you said the valence band and conduction band almost overlapping means there is no gap, because almost all the interatomic distance is completely overlapped. So there is no gap between the valence band and conduction band. So that is the reason you say that is a very good conductor. And what about the semiconductor? Maybe that Fermi gap is ordered of 1 electron volts. See, for example, like this. You take the why I go to take silicon and germanium, because it's very easy. There are 4 atoms, 4 valences there. When I go to add either trivalent or pentavalent impurities, for example, I go to take pentavalent. You know what is the meaning of penta?
5.
Pentavalent 5, trivalent 3. So I go to take this either germanium or silicon doped with pentavalent impurities or trivalent impurities. There's no doubt in the silicon. For example, I go to take pentavalent. These 4 electrons from the next to that pentavalent impurity shared with this 3p2. That is, now you get to 3p6. Are you understand this? Yes. Yes. See, due to that impurity doping, the 4 electrons, penta out of 5, the 4 is coming here. The remaining electrons, you say that is free electrons. You say that is N-type semiconductor. So in N-type semiconductor, which one is majority charge carrier? Electrons. Because that each atom, for example, I go to take doping, each atom donate 1 electrons. So n number of atoms, for example, I go to take Avogadro number of atoms. So 10 power 23 atoms. Okay, each atom donate 1 electron. You said 10 power 23 electrons are available. So that you say that N-type semiconductor, and you say that is a donor impurity. In case, for example, I go to take trivalent impurity, what happens? So here is only 4, but only 3 is available. So 1 electron is coming from where? That full energy state, valence band. So that's why it will create a holes. So now the n number of holes are created. You say that is p-type semiconductor. Are you under? Yes, 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 Nikhil. Yes, yes, yeah. That's what I'm telling. By after doping, so definitely you get that silicon or germanium doped with either pentavalent or trivalent. You get semiconductor, N-type or p-type semiconductor. So how that the formation takes place? So simply valence band, and this is a conduction band. So now you go to add a number of doping. So you have the balance, that energy gap decreases slowly. Why? Reason is that each atom, that pentavalent impurity, donate 1 electrons. So now that donor level increases. So almost the donor level is just below the conduction band. So now that band gap is decreases. Similarly, for example, holes, p-type, the acceptor level increases. Okay, so now the band gap is reduces. Maybe it will be acting as a semiconductor. Is it correct? So if the energy gap is in between the order of 1 electron volt, what is the, I think you studied in the lower classes, what is the value for silicon and germanium? What is that energy band gap? Anyone? Yes, I think you studied already. Please. So what is the energy gap for the silicon and the germanium?
0.7.
1.14.
1 point something. Yes, yeah. That is the yes 1.11 EV or 0.7. So that is the energy gap. So now that is acting as a semiconductor. You understand this? Yes. Hey, any doubts here? Any doubts or anything else here? Okay, see now this is a splitting here. See here, this is a splitting of atoms. So how why? Because they come closer and closer. So this splitting takes place. So that's in the given in the diagram. So here they are taking the example for silicon atom. That's why isolated silicon atom. The splitting of 3s and 3p states of icon is the allowed forbidden energy bands in with the energy gaps. Yes. Anything else or any doubts or anything, please? I think this is the last slide. More today's lecture. This is the last slide. Any doubts or anything, please?
No, sir.
No, sir.
Okay. If there is no doubts or any no okay clarifications, simply I go to stop the share screen. Please wait.
Please share the PDFs.
Okay. So now that PDF I will send today after 2 p.m. or 3 p.m. I will send the PPTs. No problem. These slides. Okay. See, what about any students? They elected any CR for this class representative or anyone? Yes.
Yes,
No.
sir.
Sir, Nikhil Rajan.
Yes, sir.
Yes.
2 CRs.
Oh, Nikhil Ranjan.
Nikhil Ranjan and
See, already informed in the Google Classroom. The first class itself, I told there are 3 day adults we have classes, and the timing also I already informed. No, in the first class. But why so many students are not joined today? What is the reason? But anyway, Nikhil.
Sir, I thought the class was at 1 p.m.
Hey, in the first, no, even in the first class last week, I started first class. I show the timetable. I think the which day I have class. The
Yes,
same
sir.
I go to upload in the GCR also. I will send the message. Is it correct? You check. But yesterday also I sent the message in GCR. Whether you check or not?
Yes, sir.
Yes. So yesterday, yesterday also I said tomorrow so and so day order that 5/10/2020 have a class at 12 p.m. Please all of you join by using the link. So yesterday I posted the message. Is it correct?
Yes, sir.
But still some students are missing. But anyway, the Nikhil, yes, you please inform the students. WhatsApp also I'll send the message. But anyway, today some students are missing. But anyway, in future, please understand that day order 1, okay, day order 2 and day order 4, the class timings already informed for especially for your group 2 G2. So day order 1 is 10 to 11. Is it correct? So 9 to 10 for group 1 and 10 to 11. Similarly, day order 2, so 11 to 12. Okay, today day order 4, 12 to 1. Okay, understand? So please, yes, tell me. Okay, anyway, I will share that in the WhatsApp group, no problem. Okay, yes. So because why I go to already I informed in the first class, even the first class itself, why I go to take the timing like this. So in the October 1 onwards, it start to accommodate more than 100 students in the Google Classroom. So that's why you go to splitting into 2 batches, that G1, G2. Okay, now the slight changing in the timings. I already informed, but anyway, so the students, the recorded video is there. I will upload this recorded video near Google Classroom. Please go and check. Okay. Those who are not attending the classes, please go to take use of that recorded video. Okay.
Okay, sir.
Okay, sir. Okay, ma'am. Okay. So please give your attendance quickly now.
And
So what
sir,
about
about the practical,
practical tomorrow practical class. So tomorrow,
okay.
tomorrow 3 to 4 for your batch G2.
Okay, sir.
So tomorrow 3 to 4 you have the practical, not 2:30. 3 to 4. Okay.
Okay, sir.
I will inform tomorrow, no doubt. The tomorrow class I will inform clearly, no doubt. Okay.
Sir, when we'll be taking the physical classes, so G1 and G2 would be taking classes
Separately.
like together.
Yeah. Yeah.
So
No. Always separate classes only. That is batches. For example, once we come to on campus, there are two combos, morning classes and afternoon classes like that. Two different batches. That on campus made. Okay. The- tomorrow practically we have 3 to 4. Okay. Okay. Anyway, I will send the message in the Google Classroom that I posted in the Google Classroom. Nikhil, you take care of that one. Okay. In the WhatsApp group also, I will inform. Yes, I will inform the WhatsApp group also. Okay. What about 51? 51.
Present.
Okay. 52.
Sir, leave.
Present,
Fine,
sir.
sir.
Present,
I think I
sir.
Sir,
admitted
leave.
you. Yes. 53.
Present, sir. 50.
Sir, leave क्या?
Okay. 53. 53.
Sir,
Present,
leave.
sir.
Okay.
Present, sir.
54.
Sir, leave.
54. 54. It's not there. Okay. 55. Abhinav Chaturvedi. Yes. 55 is there. Okay. 56. Arshavardhan. 56. Arshavardhan. Okay. It's absent. Okay. Margaret absent. Oh, 57.
Present, sir.
Hi Ganesh. Okay. 58. Nikhil.
Present, sir.
Okay. 59.
Present, sir.
Okay. 60. 60. Janavi. 60. It's not there. 61. Ravi Kishore. 61. Ravi Kishore. It's not there. 62.
Present, sir.
Agarwal. Okay. 63.
Present, sir.
64.
Present, sir.
Okay. 65.
Present, sir.
66.
Present, sir. Present, sir.
Okay.
66.
67. Okay. 67. 67 is not joined in the Google Classroom. I think Nikhil. Nikhil. That register number 67 is absent for all the classes. No, it's not joined. No. But in my class is not joined. Google Classroom. You just inform to that guy also. Huh? Please inform. 68. 68. Kirti. 68. It's not the 69.
Present, sir.
70.
Present, sir.
71. 71.
Present, sir. Present, sir.
72. Okay, 72.
Present, sir.
73.
Present, sir.
74.
Present, sir.
75.
Present, sir.
76. 76. I think it says 76 is the first fellow to join the Google Classroom today. Where is that fellow? 676, 77,
Present, sir.
78, 79,
Yes, sir.
80,
Present, sir.
81,
Present, sir.
82. Kunal Singh, 82, 83, 83. It's not there. 84. Ashutosh. It's not there. 85.
Present, sir.
Okay, 86. 86. Mittal. 87.
Present, sir.
88. Okay, 89.
Present, sir.
90.